Hello, can you guys hear me? Okay. All right, so I'm gonna get started in like a minute or two. In the meantime, if you guys have like any questions, feel free to either speak up through your microphone, just make sure that you unmute yourself so that I can hear you, or you can also like post in the chat. Some people have kind of already done. Okay. I am going to be recording this review, and I will be uploading the recording to our YouTube channel. So let me see here. There you go. Okay, so this is a link to the peer tutoring YouTube channel. So later tonight, or at the latest early tomorrow morning, I will have the recording uploaded, and I'll try to email everyone as well once I have the recording up so you guys will know about it. But in the meantime, that is the link to our YouTube channel, so you guys can check it out. With that said, I guess I can go ahead and get started. Okay. From what I saw, this exam is going to cover sections 2.4 to 3.4. So it looks like section 2.4 was on matrix multiplication. Let's see here. Just checking around. Okay. It looks like I'm actually missing a section. That's weird, but that's okay. So I'm going to start by talking about matrix multiplication. I don't want to spend too much time on it because I like to imagine that most of you are familiar with matrix multiplication already. And if you've kind of forgotten about it, I imagine most of you can kind of get the hang of it pretty quickly again. So as a quick recap on matrix multiplication, if you have two matrices, A and B, in order to multiply the two matrices, their sizes have to match up in a certain way. So if A is size m by k, B has to be size k by n. So like these numbers in the middle, they have to match up in order for the product to be defined. If the product is defined, then the size of the product AB, in this case, the size would be size m by n. So it's like these outer numbers, if you will, that determine the size of the product. Okay. To actually compute the product, I wrote down a couple of rules down here for how to multiply two matrices A and B. So practically speaking, I think most everyone will be computing the product of two matrices using this first rule here. So this rule says that the ij entry of AB will be equal to the ith row of A times the jth column of B. Okay. And I'll illustrate that with this example that I have prepared. There were also some ways of thinking about the product in terms of columns and rows instead of like entry by entry. So the jth column of the product AB is equivalent to matrix A multiplying the jth column of B. And then the ith row of the product AB that's equivalent to taking the ith row of A and multiplying it with the matrix B, okay? So I'm going to try to illustrate how that works with this example here. Okay. So I have two matrices here. These two numbers match up, so the product is defined. And then the size of the result will be size 3 by 6. Okay. And so I'm not going to do the entire matrix multiplication, but I'm just going to try and do enough to remind you guys of how it works. Okay. So if I want to start filling out some of the entries of the product here, the rule was to take each row of, let's call this A and let's call this B. So I want to take each row of A and I want to multiply it to each column of B. And here the product is going to be sort of a dot product of sorts. So if I take the first row of A and I do a dot product with the first column of B, that would give us 1 times 1 plus -1 times -1, and then plus 2 times 0. So you get 1 plus 1 plus 0. So ultimately that gives you 2, and that would be the first entry in the matrix here. Okay. If I wanted to get the entire first row, I would continue taking the first row of A, and again, I would do a sort of dot product with every other column of B. So I'll go ahead and complete the first row for this example. So the next entry, if I take the first row of A with the second column of B, we're going to get 1 times 2 plus -1 times 1, and plus 2 times -3. So that's 2 minus 1, and then minus 6. So I think that's going to be -5. Okay. Continue taking the first row of A. Now I will multiply it with the third column of B. So that will give us 0, minus 5, and then plus 4. So 0 minus 5 plus 4 is -1. Okay. Next, take the first row of A times the fourth column of B. So that'll give us 3 minus 1 and then minus 4. So I think that's -2. Next, take the first row of A times the fifth column of B. That'll give us 4 plus 0 plus 2. The answer is 6. And then finally, the first row of A times the last column of B will give us 1, and then like minus 3, and then plus 2, sorry, plus 4 rather. So 1 minus 3 plus 4, I think that's positive 2. And then that will complete the first row of the product, okay? Now I will kind of highlight one of the properties I mentioned here. I said the ith row of the product AB is equivalent to taking the ith row of A and then times matrix B. And if you think about it, that's essentially what we did here. We took the first row of A and we multiplied it with all of matrix B, and then that filled out the first row of the product, okay? Okay, and then let's just say as an example, if I wanted to calculate the third column in particular, so let's say the question doesn't want you to calculate the entire matrix, but just the third column of it. So to fill out the third column of the product, we would take matrix A and we would multiply it to the third column of matrix B. So to do that, we already kind of did the first row of A times the third column of B. They gave us the first entry here. We take the second row of A, and we multiply it with the third column of B. That will give us 0 plus 25 minus 2. That'll give us 23 as our answer. And then again, taking the last row of A, I multiply with the third column of B. That'll give us 0 plus 0 minus 4. So we get minus 4, and that would fill out the third column of the product. Okay. So that was taking A, multiplying the third column of B to get the third column in the product. Okay. And then just as one more example here, let's say if I wanted to calculate this entry of the product. So this would be the 3, 5 entry, because it's in the third row and it's in the fifth column. So if you want to calculate the entry in the third row and the fifth column of the product, we would take the third row of A and multiply it with the fifth column of B. Okay. So if we do that, we'll get 3 times 4 is 12 plus 0 minus 2. 12 minus 2 will give us 10. That would be the 3, 5 entry of the product, okay? So if you guys are a little bit rusty on matrix multiplication, just practice a few examples. You'll probably be good after you do a few examples, okay? Now here I've written down some of the properties of matrix multiplication. Okay. The first matrix multiplication is associative. So as long as the sizes match up so that everything is defined, then AB times C is equal to A times BC. Matrix multiplication is also distributive. Okay, so we have both of these kind of distributive laws hold. And then one of the sort of like non-properties of matrix multiplication is that it's not commutative. So in general, AB will be different from BA. So then kind of an example of some of these properties here. So if you had an expression like A plus B squared, A and B are two matrices, okay? So assuming that all the sizes match up so that everything is defined. So first, A plus B squared, we will calculate it by doing A plus B times A plus B. And then the distributive property allows us to FOIL this expression out. So if you kind of FOIL it, you'll get like A squared plus AB plus BA and then plus B squared. Okay. Now, however, though, you could not simplify this by combining AB plus BA into 2AB. So generally speaking, that would be incorrect because, as I mentioned up here, AB would not be equal to BA in general for matrices. So that means for this expression here, the simplest you could write it out, I suppose, would be this over here. And you could not simplify further by combining the AB and the BA, okay? And then there's kind of one more thing that I wanted to touch on. I figured I would mention it in this sort of section about multiplying matrices. I did want to at least talk about identity matrices. So identity matrices, these are the matrices that have 1 along the diagonal and zeros everywhere else. So this here is a 2x2 identity matrix, whereas this here is a 3x3 identity matrix. And the important property of identity matrices is they sort of act like the number 1, if you will. So if you take an identity matrix and you multiply it to another matrix A, I times A will just be equal to A. So that's kind of similar to the number 1 because you know that the number 1 times any number A will just give you that same number A again. Okay. And likewise, if you do like A times I, that will also be equal to A. All right, so that's just like a very quick overview or reminder of matrix multiplication and some of its properties, and then also identity matrices. Okay. Okay, so let's move on to another topic now. So the next thing I have lined up is elementary matrices. All right, so first, what is like the definition of an elementary matrix? So up here, I've written down one definition for elementary matrices. So an elementary matrix is a matrix that can be obtained by performing one elementary row operation on an identity matrix. So as an example here, I have a 3x3 identity matrix, and I just performed a few elementary row operations on it. So from the identity matrix, if we were to swap row 1 and row 3, that will give us this new matrix over here. So then this would be an example of an elementary matrix because it was obtained by performing one elementary row operation on the identity. Okay. Another type of elementary row operation was that you can multiply a row by a number. So for instance, if I take the identity and then I multiply row 2 by -5, that gives us this new matrix over here. So then this new matrix would also be an example of an elementary matrix. And lastly, if I were to take the identity matrix and if I perform this row operation, row 2 minus 4, row 3, the resulting matrix would be this matrix down here. So then this matrix would also be an elementary matrix, okay? So if you can obtain your matrix by doing one row operation on the identity, it is an elementary matrix. Okay. And what's important about elementary matrices is this fact that I've written down over here. Okay. So multiplying a matrix on the left by an elementary matrix has the same effect as performing the corresponding row operation. And that might not make sense to some of you, so I try to illustrate with an example here. So I took this elementary matrix from earlier, okay, and I'm multiplying it on the left to another matrix, okay. And if we do the actual matrix multiplication using like the rows times the columns, so if we work it out real quick, take the first row times the first column, you'll get 1 times A plus 0 times D plus 0 times G. And so that will just give you A. And then you multiply out the rest of the matrix. You should find that this is what you'll get for the product over here. And the key observation that I want to make is that the product is also the same it's also the same matrix that you would have gotten if you performed this row operation, row 2 minus 4, row 3, to this original matrix here. So taking this matrix and doing row 2 minus 4, row 3, it gives you the same answer as when you multiplied this matrix on the left by this elementary matrix. Okay. Okay. And then as sort of a reminder, this elementary matrix was obtained by performing this row operation, row 2 minus 4, row 3, on the identity. Okay. So when you multiply a matrix by an elementary matrix on the left, the result is the same as if you performed the corresponding row operation. All right. So that's all that I have for now, but I will be talking about elementary matrices a couple more times in some of the future sections. For now, I'll go ahead and maybe just pause and ask if anyone has any questions right now. So let's pause for a couple seconds. Yeah, so like I did last time, I will include a link to this OneNote as well. So if I'm not mistaken, I put the link in the description for the YouTube recording. And then I think I also included the link in my email when I sent out an email to everyone. So I'll do something similar this time. So yeah, you guys will be able to access this OneNote. Yeah, so to save on time, I have pre-written quite a bit. As for where it will be posted, so I will be posting the recording to YouTube, and then I will email everyone a recording of it as well. In that email, I have a link to the OneNote, and then I'll also include the link in the video description. Okay. Yeah, at the very least, I can email the notes today. As for the recording, sometimes e-learning takes a little while to allow me to download the recording. So therefore, I might not have the recording available until tomorrow morning. But if I can get it done tonight, then I will get it done tonight as well. So, okay, so to clarify, so here what we did was we took this elementary matrix and we multiplied to some other generic matrix A. So the elementary matrix, when you're doing the multiplication, it has to appear on the left, okay? If you multiply on the right by an elementary matrix, it actually does a column operation instead. But we don't really do much with column operations in this class, so for elementary matrices, you should really be multiplying on the left because that does a row operation for us. Okay. Okay. So I will move on to another topic. So I want to talk about matrix inverse a little bit next. Okay. Okay, so to start with, I kind of wrote out a definition here. So for when we're talking about matrix inverse, this only applies to square matrices. So if your matrix is not a square matrix, it will not have an inverse. Okay. So if A is an n by n matrix, we see that A is invertible if there exists another matrix B such that A times B and B times A, such that both of those are equal to the identity matrix. So if such a matrix B exists, then we see that B is the inverse of A, and then we use this notation A to the minus 1 power for the inverse of A. And here I wrote down just a few properties of matrix inverse. So this first property is A inverse inverse is equal to A. And then here there's this other property. If A and B are invertible matrices, then their product A times B is also invertible. This is assuming A and B are the same size so that the product is defined. And then we also have this formula that the inverse of AB is equal to B inverse times A inverse, okay? So just to kind of see how this works, the idea is if you just take the product AB, and if you try multiplying it with B inverse and then A inverse, what happens is, since matrix multiplication is associative, you can rearrange the parentheses and do B times B inverse first in the middle. And B times B inverse will give you an identity matrix. So it's A times I times A inverse now. And remember, the identity matrix behaves like the number 1. So if we were to do like A times I, that would just be A. So it leaves you with just like A times A inverse. And then again, A times A inverse will then give you another identity matrix. So you can kind of see how like AB times B inverse A inverse gives you the identity. And a similar computation would show you that B inverse times A inverse, and then multiplying AB will also give you an identity. So therefore, that means that B inverse A inverse must have been the inverse of AB, since it multiplies with AB to produce an identity matrix. Okay. Okay, so that's just like sort of a small proof there. Yes, so in this formula, if you will, yeah, B inverse has to appear to the left of the A inverse, so it has to appear first, if you will, okay? So if you were to ever try and say that AB inverse is A inverse B inverse, this would be wrong in general. So generally speaking, those are not going to be equal to each other. There are situations where they could be the same just by sort of coincidence, but generally speaking, they won't be equal. I don't mean to linger too much on this one point here, but I think I'll mention one more thing about this property. So this property is sometimes referred to as the dressing and undressing principle. So to kind of understand where that name comes from, The story that I've kind of read before is, so if you kind of imagine if you were like dressing yourself, and let's think about like your feet. If you were dressing up, what you would do is you would like put on your socks first, and then you would put on your shoes last, right? So that's like the process of dressing yourself is you would do socks first and then shoes second. But then when you are undressing yourself, how do you like undress your feet? Here it sort of flips though. So whereas you did socks first and then shoes last when you were dressing yourself, now when you're undressing yourself, you would actually take off your shoes first and then you would take off your socks second or last. So when you invert the procedure of dressing yourself, you reverse each process, but in reverse order as well. So that's kind of the idea of this formula when you do A, B inverse, why you have to start with B inverse and then A inverse after that. Okay. Yeah. So I'm going to do a little bit with matrix inverses. The first thing that I wanted to do is I just wanted to mention this formula for the inverse of a 2 by 2 matrix. Okay. So for 2 by 2 matrices, they are small enough that you can actually just sort of memorize a formula for the inverse. So I've written down the formula here. And then here was just sort of a quick illustration of applying that formula. So for this matrix 1, 2, negative 3, 4, the inverse of this matrix. So the formula, it was like 1 over A times D minus B times C. So that will give you 1 times 4 is 4. And then minus 2 times negative 3. So 4 minus negative 6. So that's how I got the 10 here in the denominator. And then if you look at the formula here, what we did is we swapped the diagonal entries. So A and D swapped places. So that's what I did here. The 1 and the 4, I just swapped places with them. And then for the entries off the diagonal, you just change the sign is what you do. So that's why the 2 became a negative 2, and then the negative 3 became a positive 3. Okay. So that's just sort of an illustration of the 2 by 2 inverse formula. I also wanted to cover sort of another special case right now. So talking about the inverse of an elementary matrix. So every elementary matrix is invertible. And here I've kind of written down one of the most noteworthy properties of the inverse of an elementary matrix, which is that the inverse of an elementary matrix will be equal to the elementary matrix corresponding to the inverse row operation. Okay. And I thought I would illustrate how that works with these three elementary matrices that we saw before, in just like the last section, if you will. So I had three elementary matrices here, and I'm just going to sort of quickly talk about what each of their inverses would be. So we'll start with matrix A over here. So this elementary matrix A, it corresponds to this row operation of swapping row 1 and row 3. Okay. So if you wanted to undo this row operation, what you would need to do is you would need to swap row 1 and row 3 again, right? So this row operation of swapping rows, its inverse happens to be itself, if you will. Okay. So because of that, that means the inverse of A would be equal to A again. Okay. So then here the idea is when you swap rows, to undo that, you just need to swap again. So the inverse of swapping rows is to swap rows again, and therefore the inverse of A would just be itself in this case. Okay. If we look at the second example here, so matrix B was obtained by multiplying row 2 by -5 from the identity matrix. So the inverse row operation, if I wanted to get back to the identity matrix, what we would need to do is we would now need to multiply row 2 by -1/5. Okay. So then multiplying row 2 by -1/5 would undo the operation of multiplying row 2 by -5. So these row operations, they are like inverses of each other. Okay. So the inverse of matrix B should be the elementary matrix corresponding to multiplying row 2 by -1/5. So if you go to the identity matrix and you multiply row 2 by -1/5, that would give you this matrix here, and then this would be the inverse of matrix B. Okay. And then lastly, for matrix C down here, so this matrix C was obtained by doing row 2 minus 4 row 3 from the identity. Okay. So to undo this row operation, here we would need to eliminate this -4 to get back to the identity matrix. And we could eliminate it by doing row 2 plus 4 of row 3 this time. Okay, so therefore, these row operations are inverse row operations because they undo each other. And the inverse of C would be the elementary matrix that corresponds to this row operation here. So if we were to take the identity matrix and do row 2 plus 4 row 3 on it, doing row 2 plus 4 row 3 on the identity will give you this matrix here, and this would be the inverse of C, okay? So then when you kind of look at what the actual answer was, maybe an easier or simpler way to think about it would be that here we just kind of need to change the sign from -4 to +4 to get the inverse. I guess when you're looking at this type of example, for an elementary matrix like this one here, to get the inverse, you just do like the reciprocal, like that. Okay. And then for like an elementary row swap, the inverse would just be itself then, because you just need to do the same row swap again to undo it. Okay. So this is kind of like some small examples going over how the inverse of an elementary matrix works. Any questions about that before I continue?
Wait, so for the first example with A, you're
Yes.
not like, so when you're like swapping it back, it just like it remains the same as what you're saying, like in the, for the identity.
Yeah, so so in order to undo like row 1, swap row 3, you have to do that row operation again. But the inverse matrix is, so you don't get the inverse matrix by doing the row swap to A. You get the inverse by doing the row swap to the identity. So whatever the inverse row operation is, you perform that on the identity in order to get the inverse matrix.
Okay, got
Okay, all right. Okay, so then let me see here. As for how to like calculate the inverse of a matrix in general, here there was this kind of algorithm that was discussed for finding the inverse of a matrix. So what you do is you start with your matrix A and you augment it with an identity matrix on the right. And then you need to perform a bunch of row operations until you have an identity matrix on the left. And then whatever you have on the right will end up being the inverse of A. Okay. So I will illustrate this procedure with the example that I have down here. Before I do that, just a quick remark. So in order for a matrix to be invertible, you must be able to reduce it to an identity matrix, according to this algorithm here. So therefore, you can say that an n by n matrix A will be invertible if and only if it has like n pivots altogether. Okay. So it has to have a pivot like in every row and every column, because only in that case will you actually be able to reduce all the way to an identity matrix. So then otherwise, if your n by n matrix has fewer than n pivots, it would not be invertible. Okay. So then with that, I have this matrix A over here, and I want to do one thing for now with this example is, just want to find the inverse of A. Okay, so what I will do then is I will start by taking matrix A. And I'm going to first augment it with an identity matrix. And then next, I'm just going to start performing row operations. And I need to reduce until we have an identity matrix on the left. So to start with, we have like a pivot up here. And I want to use this first pivot to eliminate everything underneath it. So we could start by taking like row 2 minus row 1. Could also do row 3 plus row 1. Okay. Okay, so then let's start by computing the rest of row 2 minus row 1. So row 2 minus row 1, that will be 3 minus 1 will give us 2 here. 4 minus 0 is 4. 0 minus 1 is negative 1. 1 minus 0 is 1, and 0 minus 0 is 0. And then here we are adding row 1 to row 3. So that will give us 0 here, 1, 1, 0, and 1. Okay? So after that, what I might do next is I might take the second row and I might multiply it by a 1/2. So let's do 1/2 times row 2. Okay. Yeah, so let's finish up this example first. So we're doing half of row 2, so you'll get negative 1/2, 1/2, and then 0. Okay. And now there's still a few more row operations that we need to do. So we need to make this one a 0. So therefore, I would maybe use this second pivot to eliminate the 1 that is above it. So let's do from here, row 1 minus row 2. So when we do row 1 minus row 2, this first number doesn't change because you would have been doing 1 minus 0. Okay. Here, this would become a 0. Here, you'll get negative 2. This would be 1 plus a half will be 3/2. This would be 0 minus a half, so minus a half. This would be 0 at the end. Okay. So that should be the new row 1. And then there's just maybe 2 more row operations that we have to do. So in order to get an identity on the left, we would now need to eliminate the 2 and the negative 2 up here. So to do that, we would use our pivot in the third column. And we will use that pivot to eliminate everything above it. So we would need to do row 1 plus 2 of row 3. And then we would also need to do row 2 and minus 2 of row 3. Okay. So performing these operations should now give us an identity matrix on the left. So whatever we end up with on the right will be the inverse of A. So let's see here, row 3 is not changed, so I'm just going to copy that one down first. And then let's try and do row 1 plus 2 of row 3. I think that would be 7/2, negative 1/2, 2. And then row 2 minus 2 of row 3. This will be negative 5/2. This will still be 1/2 here. And this would be negative 2. Okay. So then ultimately the inverse of A would be 7/2, negative 5/2, 1, and etc. It's everything that you had on the right-hand side over here. Okay. So then I believe someone wanted me to go over this remark again. Okay. Yes, so this method should work for any matrix, including elementary matrices. So that means even if what I did up here wasn't too clear to you, nevertheless, if you have an elementary matrix and you want to find its inverse, you can always find it by using this method. And it would be really quick as well because your elementary matrices are already so close to an identity matrix. You'd only need to do like one row operation really if you use this method to get the inverse. Okay. Okay. Now I do believe someone wanted me to just comment on this remark again. So here what I was saying is for a matrix to be invertible, it has to has, or for an n by n matrix at least, it has to have n pivots total. So in this example, we had a 3 by 3 matrix A, and it had 3 pivots altogether. So these would have been the 3 pivots. Okay. So if your matrix has like a full set of pivots, then it's going to be invertible. If we were missing a pivot, basically what would happen is you would actually get a row of zeros somewhere if you were missing a pivot. And then once you get that row of zeros, it's not going to be possible to get an identity matrix anymore. So if you have less than n pivots, then it's not invertible. Okay. And then, yes, that's correct. So for any matrix, whether it's elementary or not, you can always find the inverse using this method. So you would put the matrix on the left, put the identity on the right, and then do the row operation. So yes. Okay. And then there's one more kind of fact I want to mention about invertible matrices and how they relate to elementary matrices. So there's this like theorem or fact that I wrote down here that every invertible matrix can be factored into a product of elementary matrices. And I want to use the example that we did up here to illustrate this theorem or this property, okay? So to do that, I want to start by finding the elementary matrices that correspond to all of the row operations that we did. Okay. So altogether, we ended up doing 6 row operations to get to the inverse. And what I want to do right now is I want to get the elementary matrix corresponding to each of those row operations. So let's say for this first row operation that we did there, the corresponding elementary matrix, which I'm just going to call E1. Okay. So in order to find E1, what you could do is take the identity matrix and perform this row operation, row 2 minus row 1 on it, and that will give you the corresponding elementary matrix. Okay. Now,
salon.
what I've kind of seen
know.
is most of you have kind of learned that in order to find the elementary matrix here, I think most of you have kind of learned that you just put like a -1 into the 2-1 entry of an identity matrix, if you will. So you don't necessarily have to start with identity and perform the row operation. If you've just kind of seen the pattern that for row 2 minus row 1, that puts a -1 in the 2-1 entry, that's perfectly fine, okay? But like generally speaking, if you're not sure what the corresponding elementary matrix is, you just take that row operation and perform it on the identity, and that will give you the corresponding elementary matrix. Okay.
So for these elementary matrices, do we label them as like E21, E31, like depending on like what multiplier we use, or is it like E1 and E2, that sort of thing?
Right. I don't think it really matters. I know in some of your problems, they sort of asked you specifically to use like E21 or E31 as the notation. So for what I'm doing here, that's not super important. So that's why I'm just going to use like E1, E2, and so forth. Okay.
Okay, got it. Thank you.
Okay. Yeah, no problem. So then just to get the rest of them real quick. So E2, if you do row 3 plus row 1, that puts a 1 in the 3, 1 entry like that. And then the rest will look like an identity. So that's E2. For this third operation that we did, that just puts a 1/2 in the middle because you're just like multiplying row 2 of an identity matrix by 1/2. So that's E3. For this operation, row 1 minus row 2. Okay. Row 1 minus row 2 puts a -1 in the 1, 2 entry. That's E4. And then we have just 2 more operations to do. So we did row 1 plus 2 row 3, and then row 2 minus 2 of row 3. So row 1 plus 2 of row 3 puts a 2 in the 1, 3 entry. Okay, so that's row 1 plus 2 row 3. And then row 2 minus 2 row 3, that was the last row operation. So row 2 minus 2 row 3 gives us a -2 in the 2, 3 position. Okay, so these are the elementary matrices that correspond to each of the row operations that we performed. Okay. All right. Yes. What's up?
Can you hear me?
Yes. Uh huh.
Okay. So we just put the I know that so like
Uh huh.
if it's R2 minus um, R1, then you put
Uh huh.
the multiplier, which would be -1 in the 2, 1 position, right? So for um, where it says 1/2 R2, which position is
Yes.
that? Is that just like where the 1 is, or?
Right. So when you do 1/2 times row 2, like I guess you can think of it as corresponding to the 2, 2 position because that's the entry of the identity that gets modified.
Okay, thank you so
But
much. Okay.
yeah. Mhm.
Okay.
Yeah. But yeah. So generally speaking, you can always think of this as like perform the row operation on the identity, and that will give you the corresponding elementary matrix. That's like the most reliable way to do it if you're ever in doubt. Okay.
Sorry, could you repeat that if that's okay?
Yeah. So if you're ever in doubt on what the elementary matrix is, the most like reliable way that will always work is whatever row operation you're looking at. If you perform that row operation on the identity matrix, that will give you the corresponding elementary matrix. Okay.
Thank you.
All right. So then let's see here. So looking at all the work that we did now. So here we started with A on the left. Okay. And so when we perform these two row operations on A, if you remember how we talked about performing a row operation is the same as multiplying on the left by the corresponding elementary matrix. So that means if we take matrix A and we multiply on the left by E1 and E2, multiplying on the left by those two matrices will give us this matrix over here, okay? Because this is the matrix that we got by performing the corresponding row operations. Yeah, that's right, yes. And then if we kind of continue looking at the work that we did, so from this product, E2 times E1 times A, if we perform this row operation on it, it gives us this matrix over here. And performing the row operation is equivalent to multiplying on the left by the corresponding elementary matrix. So that means this matrix over here, it's taking what we had for E2, E1A, and then it's multiplying on the left by E3. So multiplying on the left by E3 would just multiply the second row by a half, okay? And then sort of continuing, so this matrix over here happens to be E4, multiplying on the left to like E3, E2, E1A. And then lastly over here, when we got to this identity matrix, this would have been the result of multiplying E4, E3, E2, E1, and A on the left by E5 and E6, since we did those last two row operations to get to the identity matrix, okay? So therefore, right now, what we have is this product of elementary matrices in the specific order of E6 times E5 times E4, 3, 2, 1. So this product, multiplying matrix A on the left, gave us this identity matrix here at the end. Okay. So the idea is that this product of elementary matrices is actually equal to the inverse of A, okay? And so if you remember, the inverse times the original, that product gives you the identity matrix. So here the idea is, since this times A gives you the identity, therefore this must have been the inverse of A. Okay.
So I solved this problem like slightly differently, and I used one less step than you. So and I got a few some of my matrices, elementary matrices were a little different. But assuming I got the right answer and I multiply all those matrices together, I still should get the like same thing you did, right?
Yeah. So to go from A to the identity matrix, there's more than one way to do it with row operations, because yeah, some people might decide to do like different row operations, right? But however you do them, as long as you got to from A to the identity, then using the elementary matrices corresponding to your row operations, then yeah, it should still give you the inverse in the end. Okay, so then that means so A inverse would be the product of these 6 elementary matrices, okay, all together written out like that. And then if A inverse, let me zoom in a bit. Okay. So then if A inverse is equal to this product, then the idea is matrix A itself, you could say that A is the inverse of this whole product of elementary matrices. Okay. And you could actually invert this product by using that undressing principle that we talked about earlier. So remember that when you apply the inverse to a product, you have to write them in reverse order. So the inverse of this product would be like E1 inverse first, and then E2 inverse second, and so forth. Okay. So then this would be A written out as a product of elementary matrices. And maybe I won't write all of it out, but I feel like it would be good to write at least some of this out. Okay. So let's go back and look at our matrices, E1 through E6, and let's talk about what their inverses would be, and I'll at least fill in some of these down here. So first, like for E1 inverse, okay. So for E1, its inverse will just be changing the -1 to a +1. So this will be like E1 inverse here. For E2 inverse, okay, the inverse of E2 would be changing this +1 to a -1. So E2 inverse will be 1, 0, -1. Whoops, 0, 0, 0, 1. E3 inverse. For E3 inverse, instead of having a half in the middle, we have to do the reciprocal. So you would have a 2 in the middle instead for E3 inverse. I guess it doesn't take that long, so let's just do the rest of them. So let me see, E4, we'll just change the -1 to a +1. That's the inverse of E4. Okay. For E5, we'll change the 2 to a -2. So it'll be 1, 0, -2. 0, 0, 1. And then lastly for E6, the inverse of E6, we'll change the -2 to a +2. So then that would be like matrix A written as a product of elementary matrices. Okay. And then this is a inverse written as a product of elementary matrices. You would just maybe need to like write out what E1 through E6 are, I guess, if you wanted to write it out explicitly. Okay. Yeah, so then for cases like E3, where you just do the reciprocal to get the inverse, essentially that would be the case when it's like one of the diagonal entries that was like modified, if you will. Yes. Mm-hmm. Okay. All right, so then I think that's kind of all that I had for this section on like matrix inverse. Well, actually, there's kind of one more thing I might have wanted to do, but no, that's okay. Let's talk about like LU factorization stuff. So the next section that I have prepared. So the LU factorization of a matrix A, that involves taking the matrix A and writing it as a product of two matrices, L and U, where U is an upper triangular matrix and L is a lower triangular matrix with ones on the diagonal. Okay. So generally speaking, your L will look something like this, and your U will look something like this, and the rest of the entries will be kind of like depending on your actual matrix. Okay. But generally, L and U will look something like that. And I thought I would illustrate how to get the LU factorization with this matrix A over here. Okay. And afterwards, I'll also talk about the LDU factorization as well. But to start with, we're just going to work on the LU factorization. Okay. Okay. So in order to get the LU factorization, what you want to do is you want to start by applying elimination and reducing your matrix A to an upper triangular matrix. Okay. So to reduce A to an upper triangular form, we would need to do row 2 minus 3 of row 1, and we'll also need to do row 3 plus 2 of row 1. Okay. Make sure when you're doing LU factorization that you are using your pivot to do all of the elimination. Okay. All right. So doing these two row operations will give us, let's see here, 1, 0, 0, minus 1, 0. Okay. So if we do row 2 minus 3 of row 1, it's going to be negative 1 plus 3 will give us 2. So we 2 again. And here row 3 plus 2 of row 1 will give us a 3. And then a 1. Okay. Now, at this point, in order to reduce this to an upper triangular matrix, what we want to do here is we want to do row 3 minus, let's see here, we'll need to do 3 halves of row 2 in order to eliminate that 3. Okay. So if we do row 3 minus 3 halves of row 2, here you'll get another 0, and then this will be 1 minus 3 is negative 2. Okay. Now, a quick comment is when you see like this matrix here, some of you might have had the impulse to do something like half of row 2, because half of row 2 would give you a bunch of 1s in the second row, which seems really nice. But when you're doing the LU factorization, you cannot do row operations of this type. And you also can't swap rows either. So for LU factorization, you have to kind of do it in this very specific way where you use like whatever pivot you end up with, and you just do elimination operations. So no multiplying a row by a number or swapping rows for LU, okay? Okay. So now that we've reduced matrix A to an upper triangular matrix, so this upper triangular matrix at the end, this will be our U for the LU factorization. Now it's really easy to get the matrix L by looking at the row operations that was performed, okay? So for matrix L, remember that for L, it has to have ones on the diagonal, at least for the LU factorization. So we can already fill in part of L, ones on the diagonal, and then it's lower triangular, so it has to have zeros up on the top, okay? As for the remaining 3 entries, they come from the row operations that we did here. Now here there's a small subtlety though, which is when we do row 2 minus 3 of row 1, that row operation will give us a positive 3 in the 2, 1 entry, okay? So I guess depending on how you write your row operations, I wrote mine as row 2 minus 3 row 1, so it kind of looks like I'm changing the sign from -3 to +3 when I put it into the matrix L, okay? Likewise, row 3 plus 2 row 1, that operation actually gives us a -2 in the 3, 1 position for L. And lastly, row 3 minus 3 halves of row 2 will give us a positive 3 halves in that position there for L, okay? So then for this matrix L and for this matrix U, that product of L times U should equal the original matrix A. Right. Any questions about that? Okay. And then I'll also talk about the LDU factorization real quick using this example. So for the LDU factorization, what you need to do is you need to, from this upper triangular matrix that we ended up with from the elimination, what we want to do is we want to take the diagonal entries 1 to -2. We're just going to take the diagonal entries and put them into a diagonal matrix, and that will give us the matrix D. And then for the U and the LDU factorization, okay, to get the new U that we need, what you do is you'll take the original U and you're just going to divide each row by its pivot. Okay. So that means in the first row, the pivot was 1. So I'm going to take the first row and divide everything by 1. So that gives us 1 minus 1, 0 again. In the second row, I need to divide everything by 2. So that will give us 0, 1, 1. And then in the third row, we need to divide everything by -2. And that will give us 0, 0, positive 1. Okay? L will be the same as before. So this L here is actually the same in both the LU and the LDU decompositions. Okay. So using that L that we found before, and then this D and this U that we just calculated, if you do L times D times U, then again, that product should give you the original matrix A, okay? All right, so questions on how to get the LDU decomposition. How do we get -1? Let's see here. This -1, I guess it was already in the original U. So what we kind of did was we divided each row by its pivot. So dividing this row 1 by 1 just gave us the same row again. So that's why you had the same 1 minus 1, 0. Okay. All right. Any other questions about this? Okay. So that's like a sort of a quick example on LU and LDU decomposition. So then, of course, we also want to review how to use the LU factorization to solve an equation. So if you're given an equation AX equals B, and you're asked to solve it by using the LU factorization of A. So first, in this equation, AX equals B, we can replace A with L times U, since A would be equal to LU. And then to solve for X, what we're going to do is we're going to take the product UX and think of it as like a new variable Y. So Y would be equal to UX. And then you'd have Ly equals B. And you're going to start by solving this equation, Ly equals B, using forward substitution. Once you solve for Y in the first step, you can then use it in the second step to solve for X in this equation, Ux equals Y. And you would solve that by doing backward substitution instead, okay? So to illustrate how that works, I have this example here already. So we had the system of equations, and if we were to write it in matrix form, you'd have 1, 3, minus 2, minus 1, minus 1, 5, 0, 2, 1, multiplying xyz equals 1, 1, and negative 1. Okay. So here's our equation in the form like A, x equals b. Okay. And this matrix A that we have here, it is the same as the matrix A that we used in the previous example. Okay. So we already found the L and the U for the LU factorization. So in order to solve this equation now, the system of equations, I'll follow the kind of two-step process that we have outlined over here. Yeah. So first, the first step is to solve the equation Ly equals B. So I'll go ahead and write it out. So L was 1, 0, 0, 3, 1, 0, negative 2, 3 halves, and 1. So that's L times Y. And for Y, we'll just use maybe like Y1, Y2, Y3 for that. So Ly equals B, which is 1, 1, and minus 1. Okay. And because L is a lower triangular matrix, if we were to like convert this into a system of equations, the first row gives us the equation 1, y1, plus 0, y2, plus 0, y3 equals 1 on the other side. The second row gives us the equation 3y1 plus 1 y2 plus 0 y3 is 1, and then The third row is negative 2y1 plus 3 halves y2 plus y3 equals negative 1. So because L was lower triangular, you can solve this system of equations using forward substitution. So we already know y1 is 1. So substitute into the next equation. So you'll get 3 plus y2 is 1. So y2 will be 1 minus 3, so it'll be negative 2. Then substitute y1 and y2 into the third equation. So you'll get, let's see here, negative 2 times y1 plus 3 halves times y2 plus y3 will be negative 1. So using this to solve for y3, be 1 plus 3. I believe y3 will be equal to 3, okay? Okay, so you solve for y1, y2, and y3 by doing this forward substitution. Then after that, you still have one more step, which is to go back to the equation ux equals y to solve for the vector x, okay? So here we're going to write that out. So u was, let's go back to the previous example. So we're using the u and the lu factorization, which would be this u over here. That's 1 minus 1, 0. 0, 2, 2, and 0, 0, negative 2. That's u times x, x being just the original x, y, z. Ux equals y, and we just solve for y, so y1 is 1, y2 is negative 2, and y3 is 3. Okay. So then we just need to convert this into a system of equations. So this will give us 1x minus 1y plus 0z is 1. It's the original u, because this is LU, not LDU. So we're using the LU factorization. And then let's see, so this second row gives us 2y plus 2z will be negative 2. And then the third row gives us negative 2z will be equal to positive 3. And then from here, we can just, again, do back substitution real quick. So z will be negative 3 halves. Okay. Z is negative 3 halves. Y is going to be, I think y will be positive 1/2, I think. So sub negative 3 halves in for z, be negative 3, so added over 1/2, okay? So y is 1/2, and then if y is 1/2, you can substitute that into the first equation. X will be 1 plus 1/2, so x will be 3 halves altogether. So then this should be the solution to the original system of equations, okay? All right, so any questions on how we solved the system of equations using the LU factorization? Sure, so so in that example, we were using the LU factorization to solve, so that's why we were using this U over here. This is the new U from the LDU factorization, which we did not use. Okay. And then there's kind of one more thing I wanted to discuss related to LU factorization, which was oh, okay. There's more than one thing that I wanted to discuss. So, as I mentioned earlier, when you're getting the LU factorization, you are kind of restricted on the types of row operations that you can perform. So the only types of row operations you can perform is elimination type operations using your pivots to eliminate. So I mentioned how you can't just multiply a row by a number. And I also mentioned that you can't swap rows, okay? So if it is not possible to reduce A to an upper triangular matrix without doing any row swaps, then that means an LU factorization is not possible. Okay. So instead, if a row swap is necessary, then you can get this PA equals LU factorization instead. So I kind of just wanted to illustrate how that works with this example over here. Okay. So if we look at this example, and let's say we wanted to find the LU factorization, what we would do is we would do row 2 minus 2 row 1. I guess you'd also do row 3 plus 1 of row 1. That would eliminate everything in the first column that you needed to eliminate. But when we take a look at the second row, row 2 minus 2 row 1, you actually get this 0 in this pivot position here. Okay. And because we get this 0 here, we're not able to proceed any further to get the LU factorization. So this is no good. You can't get an LU factorization with this. Okay. Now, however, though, you can notice that if you just swapped row 2 and row 3, you would end up with an upper triangular matrix. Okay. However, that row swap affects things so that you no longer have an LU factorization, okay? So in order to get this PA equals LU factorization, okay? So to get the PA equals LU factorization, what you need to do is you need to perform your necessary row swaps first before you do any elimination, okay? So then what I would recommend for this example is we saw that we have to swap row 2 and row 3 in order to reduce it to an upper triangular matrix. Okay. But to get to PA equals LU factorization, we need to do that row swap at the beginning. So that means I'm going to start from the original matrix, and I'm going to first do row 2 swap with row 3. Sorry, row 2 swap with row 3. Excuse me. Okay. So we now that we did that row swap, then we'll then proceed with elimination as usual. So we'll do like row 2 plus row 1 this time. And this time we'll also do row 3 minus 2 of row 1. Okay. Okay, so this time row 2 plus row 1 will give us a 1 and a 4. And then row 3 minus 2 of row 1 will give us a 0 and a 3 here. Okay. So then looking at the work that we did here, so if we, what we can do here is we can take this matrix U, this upper triangular matrix, and then from the elimination operations that we did here, we can construct the usual matrix L that has ones on the diagonal. And we would then like sort of change the sign of the numbers that we used in our row operations to get the rest of the entries. Here we never did an operation of the form like row 3 plus or minus something row 2. So if you never do any of those row operations, you just put a 0 in that corresponding entry for L, okay? That's your L. This is the U that we have, okay? So this product of L and U, it won't be equal to the original matrix A, but rather this L, this product of L and U, it's essentially an LU factorization for this matrix over here. Okay. Now, if we think about what this matrix is, this was matrix A, but then with a row swap performed on it. So that row swap, equivalently, we can think of the row swap as having come from multiplying A on the left by the corresponding elementary matrix. Okay. So that means what we want to do is we want to find the elementary matrix that corresponds to this row swap that we just did. Okay. So to get the corresponding elementary matrix, we just need to perform this row swap on the identity. So take an identity matrix and just swap rows 2 and 3. That gets us the matrix P. So this matrix here would have been P times A. And so what we essentially did is we found an LU factorization for PA, okay? And that's how you get the PA equals LU factorization. Yes,
Can you hear me?
yes.
Okay. So to find out which row swap exactly to do, would you have to first go through um, the whole elimination like you did, just like to see, and then which row swap to do first?
Yes, at least I would say yes. So
Okay.
especially if the numbers aren't too clear initially, then it's maybe not clear whether you even need to do a row swap first, but if as you're performing your elimination, you find that you get a 0 in like one of your pivot positions and aren't able to proceed anymore, then that would tell you you have to do some kind of row swap. Okay.
Oh, okay. Actually, yeah, that makes sense
Uh-huh.
because you only need the PA equals LU if you can't get to the A equals LU in the first place, right?
Right, right.
Okay. Thank you.
So yeah, the example that it did here was maybe a little bit more difficult in the sense that it wasn't necessarily clear at first that you would have needed to do a row swap. So Sometimes when you're given these types of questions, sometimes they make it obvious that you have to do a row swap first. So for instance, if this was what you were given initially, it's making up some numbers. So if you were given this initially, then you would immediately see that you needed a row swap because you can't do anything with a 0 here at first. So in a situation like this, I guess it would be obvious you have to do a row swap first. But yeah, in a case where like this one, it's maybe a little bit harder to see that a row swap was necessary until you actually did the row operations. Okay.
Thank you.
Okay. And then I guess there's one more kind of related notion, which is this LDL transpose factorization. So the LDL transpose factorization, this is a factorization that only works for symmetric matrices. And to kind of recall some related notions, so first to recall what the matrix transpose was. So given some matrix, its transpose, all you do is you rewrite it so that the rows become the columns. Like row ABC is now column ABC here. DEF, just flip it and make it vertical. Likewise, the third row GHI became the third column, okay? So that was the operation of transposing a matrix. All right, and then a matrix A is set to be symmetric if its transpose was equal to itself, okay?
Wait, I don't know if I'm remembering this wrong, but I feel like there was this, I think it was with the transpose, where like you flip items along the diagonal or something like that.
Yeah, so that's equivalent to what happens here, right? So like B and D swap places, C and G swap places, and then the F and the H swap places, right?
Right. So,
Mm-hmm.
but what if it's not like, what if you don't have like D and D? Like, what if they're different numbers? Would you ever swap it?
Well, yeah, so like if you're just given like any matrix, let's see here. Yeah, so if you're just given like any matrix and you're asked, what is its transpose? So yeah, the transpose of this matrix, you can think of it as like reflecting across the diagonal. Okay. Or
Oh, okay.
equivalently, the rows are becoming columns, yeah. Okay.
Okay.
Or columns are becoming rows. So those are all different ways of looking at it. Okay. I guess maybe one thing that's maybe worth noting is you can transpose like any matrix. It doesn't have to be a square, right? So for instance, you could transpose this guy. So in this case, the way you would transpose it is you would think of it as making the rows columns or making the columns rows. Okay. So I guess if your matrix isn't square, then the reflect across the diagonal way of looking at it breaks down, if you will. It doesn't quite work. Okay. Okay. And so then for a matrix to be symmetric, so it has to be equal to its own transpose. What that actually looks like is basically that means your matrix needs to be the same across its diagonal. So something like this would be a symmetric matrix. Okay. All right. So then to get the the LDL transpose factorization for a symmetric matrix, the LDL transpose decomposition is actually the same as the like LDU factorization. So it's just that when your matrix is symmetric, the U turns out to be the transpose of the L if your matrix is symmetric, okay? So then to kind of illustrate, I have a symmetric matrix over here. So you'll notice this guy, it is the same reflected across its diagonal. So it is a symmetric matrix. And just to find the LD, L transpose decomposition real quick. So what we'd want to do is we'd want to reduce A to an upper triangular matrix. So here we'd start with row 2 plus 2 row 1 and row 3 minus 3 row 1. Okay. So let me see, row 2 plus 2 of row 1, that'll be a 3 here. This would be a 6. Row 3 minus 3 of row 1, this would be a 6, right? And then this would be a negative 5. We would do one more row operation. We would do like row 3 minus 2 of row 2. And that will give us an upper triangular matrix in the end. This would be negative 17. So then from here, the L that we would have gotten based off our row operations. So we'd have a negative 2 here, positive 3 here, and then positive 2 here, okay? So that would be the L. So then for the D, to get the D from the like LDU decomposition, remember that you just take the diagonal entries of your upper triangular matrix and just put them into a diagonal matrix like this. Okay. And then remember that to get the new U for LDU decomposition, the rule was to take the first U that you found and divide each row by its pivot. So you would divide row 1 by 1, divide row 2 by 3, and divide row 2 by negative 17. And what you'll notice is that this U happens to be the transpose of our L, okay? Well, so I guess like this, let's see here. 1 second. Okay, sorry, my computer is sometimes weird. So this is the original U. This is the U that you need for the like the LDU decomposition down here, if you will. Now, in a sense, though, you don't really need to calculate the new U because, as I was kind of mentioning, so your new U is going to be the transpose of your L, at least if your matrix is symmetric, okay? So then in D, all you really need is your L and your D to get the LDL transpose decomposition, okay? And then the idea is your U is actually L transpose, and that's why it's LDL transpose instead of like LDU. Okay. All right. Any questions about that? Mm-hmm. Okay. Then let's see what else do we have. Okay, so we'll talk a little bit about vector spaces and subspaces. So a vector space is a set of objects that can be added and scalar multiplied. And vector space has to satisfy like certain axioms. You guys might remember like a giant list of axioms for a vector space. Here I've kind of listed some of, I guess, like the axioms kind of written out, if you will, down over here. I don't think you actually need to, whoa, okay, sorry. Like I said, sometimes my computer is weird. But I don't think you guys need to actually like memorize the vector space axioms, but I did just kind of list them here for completeness. Okay. In this class, though, what's more important is to know what a subspace is, if you will, rather than like what a vector space is. So if you're given a vector space V, and then let's say you're given W, which is a subset of vector space V. Okay. So W is going to be a subspace of V if it satisfies these two conditions that I've written out. Okay. So first is that W has to be closed under addition. Right. So what it means for W to be closed under addition, that means that if you take any two vectors like W1 and W2 in W, their sum W1 plus W2 must also be in W. So that's what it means to be closed under addition. And then the second property that has to be satisfied for subspaces is that they have to be closed under scalar multiplication. So if, say, W1 is a vector in W, and if K is any scalar, then K times W1 has to be in W as well in order to be a subspace, okay? Yeah, so I kind of figured this was is probably where people would start getting confused, generally speaking. Now, I only have at least one example prepared, though, for this review. So let's take a look at this example that I have. Oops, that's not what I want. Okay, all right. So here we have this set W. So W is a subset of the vector space R4. And W specifically is like all vectors satisfying this property that x1 plus x3 will be equal to x2 plus x4, okay? And then the question is W a subspace of R4? So before we get to working out the problem, I just want to kind of take a closer look at the definition of W. So for a vector to be in W, it has to satisfy this condition here, right? So I just put it like as a small example real quick before we start working through the actual question. So it's sort of like a sub example. So if I do like 1, 2, 3, 2. Okay. So this vector, this is an example of a vector that is inside of W. Okay. Because if you take the first and the third component, it's 1 and 3. X1 is 1, X3 is 3. So X1 plus X3 is 4. But then if you take the second and the fourth components, X2 and then plus X4, that's going to be like 2 plus 2, which is also equal to 4. Okay. So for this vector, you see that like X1 plus X3 is in fact equal to X2 plus X4. So because that property is satisfied, And that's why this vector is inside of the set W right now, okay? Whereas in contrast, something like this vector here, so this is an example of a vector that is not in W. Because for this vector, the first and the third components added up is not equal to the second and the fourth components added up. Because here, if you add the first and the third components, that's 2. If you add the second and the fourth components, that's a 0. See? So because this condition, because these are not equal to each other, that's why this vector is not in W, okay? So this is just sort of like trying to make it a little bit more clear, like what does this like notation mean, if you will. So this is defining like which vectors in R4 are inside of W. To be inside of W, the vectors have to satisfy this condition, okay? All right, so then to get to like the actual question, to check if W is a subspace, we need to check if W is closed under addition, and also is it closed under scalar multiplication. So let's take a look at the closure under addition property first. So we need to take 2 vectors in W right now. So let's say that we have 2 vectors W1 and W2. And let's say W1 is, let's see here. Let's say W1 is like X1, X2, X3, and X4. Okay. And then let's say like W2. W2, since it is not necessarily equal to W1, I might use like new variables. So like Y1, Y2, Y3, and Y4 for W2. Okay. So we have these 2 vectors, and we are assuming that these 2 vectors are inside of W right now. So therefore, we are assuming that like x1 plus x3 is equal to x2 plus x4. And likewise, we are assuming that y1 plus y3 is equal to y2 plus y4, okay? Because these conditions should be satisfied if these vectors are inside of W. Now, to check closure under addition, what we have to do first is we have to add our 2 vectors. So we have to compute W1 plus W2 next, okay? So to add the 2 vectors, it's just the usual addition. So W1 plus W2 will be like x1 plus y1, x2 plus y2, x3 plus y3, and x4 plus y4. Okay. So that's the sum W1 plus W2. And now that we have the sum, to check closure under addition, we need to check is that sum of W1 plus W2, is it inside of the set W, okay? So to check if this vector is in W, we need to check if it satisfies this defining condition for W up here. Okay. So we need to check if we take the first component of the sum plus the third component we need to check if this will be equal to the second component plus the fourth component. Okay. So if these are actually equal to each other, then that would mean that the sum is in W, and that W would be closed under addition. And if we can show that these are like somehow not equal to each other, then that would prove that W is not closed under addition then, okay? So in order to check if this is true or not, we have to make use of our assumptions about W1 and W2 over here, okay? So we know that like x1 plus x3 should be the same as x2 plus x4. And then likewise, we know that y1 plus y3 should be the same as y2 plus y4. So with that information in mind, what I might do here is I might take x1 plus y1 plus x3 plus y3, and I might rearrange the terms in this equation. So I'll rewrite this so that I group together x1 plus x3, and then I'll group together the y1 and the y3 terms. So all I'm doing is rearranging the terms right now, okay? All right, now from here though, using this assumption that we have, knowing that x1 plus x3 is equal to x2 plus x4, that means in this expression here, I can like substitute or replace x1 plus x3 with x2 plus x4. Okay. So I can do that because I know that these two are equal to each other. Okay. And then likewise, we know that y1 plus y3 is the same as y2 plus y4. So therefore, I can replace y1 plus y3 with y2 plus y4. Okay. So then looking at what we have starting with x1 plus y1 plus x3 plus y3. We've managed to prove that it's equal to x2 plus x4 and then plus y2 plus y4, okay? So we've proven that this condition is actually satisfied. Okay, let's see here. And so this condition, oh geez, hold on. What's wrong with my computer? Oh, there you go. Wow. Okay. Yeah, my stylus stopped working for a little bit, but it seems to be okay now. So we proved that this is true. Okay. Okay. So then, since we proved that that was true, that proves that W1 plus W2 is still inside of the set W because it satisfies that condition for being in W, okay? So right now we've proven that W is closed under addition then, okay? Okay. Now that's not enough to say that W is a subspace though, because to be a subspace, we also need to prove that's closed under scalar multiplication as well, okay? So that will be kind of like the next thing that we check. So I'll do that down here. No, so it is true that every subspace has to have the zero vector in it, but it is not true that you have to like check that the zero vector is in the subspace. So for subspaces, you only need to check these two conditions: closure under addition and closure under scalar multiplication. Whoops. Okay. If your subspace is closed under scalar multiplication, so that means you can take, so just like kind of to see what's going on. So if W is closed under scalar multiplication, you can take a vector that's inside of W, and we should be able to multiply by any scalar. So I can multiply W1 by the scalar 0. And according to this property, this must also be in W as well. But then of course 0 times vector W1 is just the 0 vector. So being closed under addition will sort of automatically imply that the 0 vector is inside of your set. So that's why you don't need to actually check it, because you kind of get it for free once you've proven that it's closed under scalar multiplication. Okay?
Sorry, can you hear me?
Yes. Yes.
I didn't understand that last part where you say like you can just assume that it's in W. Like I didn't understand that.
Let's see here. Talking about the 0 vector, you mean?
Yes, sorry about that. Yeah.
Yeah. So you don't need to actually like specifically check that the 0 vector is inside of your set. So once you've proven that your set, well, so assuming that you are able to, so like if your set is closed under scalar multiplication, then like once you've proven that it's closed under scalar multiplication, you kind of get like as a freebie, if you will, that the 0 vector is inside of your set as well. Because being closed under scalar multiplication sort of automatically guarantees already that the 0 vector is inside of your set. So therefore, you just need to check that's closed under scalar multiplication, and that is already enough to conclude that the 0 vector is in it. Okay.
Oh, okay. So, don't we need to check right now, like if it's closed under the scalar multiplication? Or...
Yeah. So in the example, we still need to check that's closed under scalar multiplication. We haven't done that yet. Yeah.
Oh, okay. Oh, okay. Okay, that makes sense. Okay.
Okay. Yeah. So then, as for checking in this example, that's closed under scalar multiplication. So for this, we start with a vector in our set. So starting with W1, we can assume that it was the same as it was before. So let's say W1 is x1, x2, x3, x4, and we're going to assume that it satisfies this condition, that the first and the third components added up is equal to the second and the fourth components added up. Okay. Yes. So then, assuming that this is true, what we want to do is we want to now multiply this vector by a scalar. So I'm just going to multiply by some k. And that gets us kx1, kx2, kx3, and kx4. Okay, so then we want to check if this vector is inside of W. Okay. So to be in W, that means that the first and the third components added up must be equal to the second and the fourth components added up. Okay. And we can prove that this is true by using this assumption up here. So assuming that so then assuming that this is true, if you just multiply both sides by k, then that means k times x1 plus x3 would have to be equal to k times x2 plus x4. And I guess if you distribute the k, then you get kx1 plus kx3 must be equal to kx2 plus kx4. Okay. So that means like this condition will check out. If w1 was in w, we see that kw1 is also in w for any scalar k. So then that proves that w is also closed under scalar multiplication.
Sorry, would it be possible to
Yes.
explain this again, if that's okay?
Yeah. So with closure under scalar multiplication, you want to start with a vector that's inside of your set already. So we have this vector w1, which we're assuming is inside of w. So therefore, we're assuming that it satisfies this defining condition to be inside of w. What we do is we multiply it by scalar. So multiplying by k gave us this new vector here. Okay. And then the question was, is this new vector inside of w? So for this vector to be in w, it has to satisfy this condition here. Its first and its third component added up must equal its second and its fourth component added up. Okay. So we proved that this is true by using the fact that w1 is in w. So we have this equation is true. So then we just took what we knew and we multiplied both sides by k. And that kind of proved this result, that this equation is true down here. Okay. So that, from there, that proves that w is closed under scalar multiplication. And then since w was both closed under addition and closed under scalar multiplication, so therefore that makes w a subspace.
So I have two questions.
Yes.
So when it comes to could you go, yeah, so it says it's asking is W a subspace of R4, right? So
Right.
I don't know, maybe it's just because I feel like I've seen some homework problems that ask about like subsets and stuff like that. So when it asks about subsets, it's probably referring to subset of like R to the N, like some R like 4 R.
Something like that, right? Yeah.
Okay.
Right.
So basically, like you're always trying to show it's a subspace of something like R to the N, right?
Well, I guess it's not always going to be an R to the N. So I'm pretty sure you guys had an assignment involving like matrices,
Uh-huh.
like showing that something is a subspace of like the space of all 2x2 matrices or something like that. So you guys have had, I think, a few questions involving like spaces of matrices instead of just like an Rn.
Oh, right, yeah. And then also when it comes to like
Yeah.
proving like closed, because the thing is, I don't know, I'm like never 100% sure when it comes to like proving closed under addition and multiplication. Like I don't know if I like showed enough, you know what I mean? Do you just try to like formulate your answer like so like so it's like in the same I don't know how to say this, like in the same written the same way like the original um condition was? Like is that like the whole
Yeah,
eventually
I,
like
I think I get what you're saying, and essentially yes. So here, like, so whenever you have these problems, there's gonna be some kind of a condition to be inside of like your set that you were given. So here, in this example, the condition was that the first and the third components added up must be equal to the second and the fourth components added up. So then to check closure under addition, you assume you have two vectors that satisfy that condition. You want to check if their sum also satisfies that condition. That's kind of like a very general description of like what you would do in any problem. And the scalar multiplication is like, suppose you have a vector that satisfies that condition. If you multiply it by a scalar, does that result still satisfy, that condition? Okay.
Okay, got it.
Okay. So I do want to try to wrap this up by 7, just because it kind of sucks, I think, to sit in front of a computer for so long. So I'll give you guys sort of an option at this point. So we can do another subspace example involving matrices. Instead of like in this case, we were using R4 or Rn. So you can maybe do an example with matrices. The other option is to move to one more topic. And I think between what I have left, I would maybe jump to nullspace as the final topic and skip columnspace. I have some notes for columnspace written already, so you can look at it when I provide the OneNote. I was thinking I could either jump to nullspace or I could do another subspace problem. So what do you guys want? I see one vote for another topic, but okay, all right. 2 votes, I guess that trumps 0 votes for. So okay, so I think it'll be good to maybe go on to one final topic. So I wanted to maybe go on to nullspace because I think nullspace is not that difficult of a topic. So you can probably knock that out with the time remaining for the most part. Okay, so given an n by n matrix A, so the null space of A is defined to be the set of all solutions to the equation AX equals 0. Okay. And in order to find the null space of a matrix, it's in some ways, like depending on how you think of it, I guess it's easiest to find the null space of a matrix if you reduce the matrix into this reduced row echelon form. Okay. So I wanted to kind of illustrate with this example here of reducing a matrix to the reduced row echelon form, and then from there finding its null space. And here I wrote down the conditions that have to be satisfied to be in reduced row echelon form. Okay. But I'm just going to go ahead and start working through the example, and we can kind of point out those conditions once we get to it. Okay. So I do want to just start like row reducing right now. And we're just going to kind of do it the usual way at first. So here I would eliminate everything in the first column. So I would do like row 3 plus row 1, and I'll do row 4 minus row 1. Let's work out the rest of row 3. So we're adding row 1 to row 3. And then we're subtracting row 1 from row 4. Subtracting row 1 from row 4. So I think that's what we get there. Okay. So from here, now we move on to the second column when we have our new pivot over here. Okay. And I'm gonna just eliminate everything underneath it for now. So I'm gonna do like row 3 minus 3 row 2. And I'm also gonna do row 4 plus row 2, okay? Now, I'm also going to do one more thing here, which is for the reduced row echelon form, one of the requirements is that you need to have a 0 above and below each of your pivots. Okay, so above and below. So that's kind of a new requirement for the reduced row echelon form. So these two row operations will give me zeros beneath this pivot, but I need to get a 0 above it as well, meaning I'd also want to do row 1 minus row 2. Okay. In order to get zeros both above and below my second pivot. Okay. So let's work out the rest of our new matrix here. So when we do row 1 minus row 2, this would be -1, -3, and -5. Okay. Row 3 minus 3, row 1, this is another 0. This is -7. This is -8. Not very pretty, but that's okay. And then row 4, did I do that right? Yes, okay, I think I did that right. And then row 4 plus row 2 is 0, 2, 4, and 8. Okay. Okay, so hopefully I haven't made any mistakes. It's not a big deal if I did make a mistake, I suppose. As long as you guys still kind of understand the process, I think that's good enough. So let's kind of continue. So right now I'm kind of missing a pivot in this third position. Okay. But I can easily swap rows in order to get a pivot up there. So I think that will be my next step is I will just swap rows 3 and 4. Oops, swapping. So you'll get 2, 4, 8. And here you get 0, 0, 0, -7, and -8. Okay. So then, let's see here. Swap row 3 and then row 4. So then what I'll do here is in the third row, I'm going to go ahead and just multiply the third row by a half. So I'm going to do half of row 3. So on the one hand, that's nice because every number in the third row is actually divisible by 2. It's also worth noting, though, that for the reduced row echelon form, it is a requirement that all of your pivots must be like equal to +1. So even if the numbers weren't all divisible by 2, at some point I would have needed to multiply the third row by half anyways, because I would have needed a +1 as a pivot in the end for the reduced row echelon form. Okay. Okay, so now that I have this is taking a little bit longer than I expected. I think I might have made a mistake somewhere. So just like as a heads up, if you're going through the work and you're getting different numbers, it is possible I made a mistake, but that's okay. So here, now we do need to get zeros above our pivots as well as below, okay, as I mentioned earlier. So what I'd probably do at this point is take my third pivot that we have here now, and I would eliminate everything above it. So I'm going to go ahead and do row 2 minus row 3 to get rid of this one here. And also do row 1 and plus row 3 as well. Okay, so we're getting closer. Let's just work out the rest of the matrix. So we're doing row 2 minus row 3. So that's a 0. It's a -1 here. And then we're doing row 1 plus row 3. That's a -1 and another -1 there. Okay. -7 and -8. So I guess just a few more things. So we have a fourth pivot over here. And so what I'd probably do at this point is I would probably just multiply the last row by -1 over 7. Because we have to have a +1 instead of a -7 for a pivot for the reducible echelon form. Okay. And the last thing that we have to do is using this new +1 pivot, if you will, we just need to eliminate everything above it because you need to get zeros above all of your pivots as well as below. So lastly, we will take row 3 minus 2 of row 4. We'll also maybe do row 1 plus row 4. And that will eliminate the -1 and the 2 in that fourth column. So then this will be the reducible echelon form now. Okay. I'm just going to work out the last entries. So row 3 minus 2 of row 4. It's something like 12 over 7, I think. And if we do row 1 plus row 4, I think that's 1 over 7. Okay. So I did that kind of quickly. So I think it's quite possible that some of my numbers are a bit off, but let's just assume that this is what we got at the end. Okay, so this would be the reduced row echelon form. So in order to get the null space of A from here, okay, so I guess everyone kind of has maybe like a slightly different procedures at this point for what they do to get to the null space. It all works out the same in the end, but just to kind of clarify, people will do maybe slightly different things at this point. So I'll just kind of show you guys like the way that I myself do it. So I want to convert this into a system of equations. Okay. So looking at each row is going to give me an equation. The first row will be like 1x1 plus 0x2 plus 0x3 plus 0x4 and then like plus 1 over 7 x5 at the end. And we want to set this equal to 0 because the null space was specifically solving ax equals 0, which means for null space, you should have 0 on the right-hand side, okay? Likewise, for the second row, that will give us the equation x2 minus x5, and then we set it equal to 0 for null space. We get x3 plus 12 over 7 x5 equals 0. And then lastly, we do have x4 plus 8 over 7 x5 equal to 0, okay? So what's happening in this example is we have these 4 equations here at the end. So because we have 4 equations, that's going to allow us to solve for 4 of our variables, okay? So 4 of them we can solve for, and then the other variable would be what we call a free variable. And there's sort of a convention that we tend to follow in this class, which is we solve for our pivot variables. So in this problem, the pivot variables would refer to x1, x2, x3, and x4, because those were the columns that had the pivots in them. So then the columns without pivots would correspond to your free variables. So here in this example, x5 is the only free variable that we have, because the 5th column was the only column without a pivot. Okay, so what we'll do is we'll solve for the pivot variables, and the way that I handle the free variables is I assign to each free variable a parameter. Okay. So x5 is the only free variable, so I'm going to set it equal to another variable. So I tend to use letters like R, S, and T. So I'm going to use T. So I'm going to say x5 is T. So x5 can be like any real number. So to represent that, I'm just going to denote it with a variable. So the idea is T could be any number. So in this sense, this is why x5 is a free variable, because it's like free to be any value. But then with that, I'm now going to solve for the rest of the variables using the equations that we have. So here we can easily say that x4 will just be negative 8 over 7 times x5, where x5 is t. Likewise, x3 is just negative 12 over 7 times x5, which is t. x2 will be equal to x5, which is t. And then x1 is negative 1 over 7 t. Okay. All right. So then t can be any real number. So usually what I do is I'll rewrite this in vector format, because when you're looking at like the solutions to ax equals 0, the solutions will be referring to like the vector x. So therefore, I just want to rewrite my x as an actual vector in the end. So here we have vector x will be equal to, and then something else I like to do is I like to factor out the parameter t from the vector that we get on the right-hand side. So I would write it like this. It's not necessary to do this, I suppose, but it is nice to do. Okay. And then t can be any real number, as I said earlier, so it might be nice to write something like this just to indicate t can be any real number. So then this would kind of be what the null space of our matrix A is. It is the set of all multiples of this one vector here. And another way that you could write your answer is when you see that the null space is all multiples of this single vector, you could also write it and say that the null space is the span of this one vector then. Because it's like this one vector spans the whole null space. So write it as like a span. Again, you don't necessarily have to do this, but you can. This is like another way you can write out the solution for what is the null space. So that's kind of the idea of finding null space from the reducible echelon form. So if I were to kind of try to summarize real quick, once you reduce your matrix into the reducible echelon form, the way that I do things is I convert the RREF into a system of equations. I identify which of my variables are the free variables by looking at which columns are missing a pivot. I'll assign a parameter to each free variable, and then I'll solve for all of the pivot variables, if you will, in terms of that parameter. And then lastly, I write my solution in this sort of vector format. Okay. So I'm a little bit over time. I'll go and do one more thing real quick, just to give you guys just a little bit more practice on null space and reducible echelon form. Yeah. So I kind of wanted to address that question there, if you will. So let's say like as a hypothetical.
Wait, sorry. I have one question about it.
Yes. Yes.
So if you had like that t and that vector, and then like you said like plus or like there was another vector, like you were adding another vector for that.
Yeah.
Then that other vector would also be in the span of the null space, right?
Yeah. So that's kind of what you guys are asking about. So if I were to sort of create an example right now, just real quick to show you guys how that will look. So basically, if you have more than one free variable, what's going to happen? So my intention was for the previous example to illustrate that, but either I messed up in my row operations or I might have messed up in creating the matrix itself at the beginning. So let's pretend that like this was your RREF instead. Okay. So we'll just kind of do this real quick, and then we'll see what the null space looks like. So in this case, you have 3 pivots. So one pivot here, here, and then here. So yeah, so in this case, x3 and x5 would be the free variables in this case, because you're missing 2 pivots now, so you have 2 free variables. So when we write out the corresponding system of equations, so the first row will give me this equation, second row will give me this equation here. The third row will give us x4 minus 3, x5 is 0. Yeah, so what I tend to do is I parameterize each of the free variables. In this case, we'll use 2 parameters, one for x3 and one for x5. So I'm going to use s and t. Then we'll solve for the remaining variables again. So here, x1 will be minus s minus t. If you move the x3 and the x5 over. S. Okay. X2 will be positive s and then plus 2t, moving everything to the other side. And then here, x4 would be 3t is what you'll get. So when I write this out in the vector format, so again, like I myself will write it in a particular way. So here, this time I'll write it as a linear combination of 2 vectors. S and t are going to be the coefficients. And there's different ways of thinking about it, but I guess for me, the simplest way for me to think about it is I'm just going to take all the coefficients of S in each of the equations, and those will go into this first vector. The coefficients of T from each of those equations will go into the second vector. Okay. S and T can be any real number. So here your null space is the set of all linear combinations of these two specific vectors. And then, yeah, in terms of span, you could say that it was the span of those two vectors now. So the span of -1, 1, 1, 0, 0, and -1, 2, 0, 3, 1. Okay. All right, yes.
So do we only have the equations, like for the system of equations, for the rows that have the pivots?
I guess essentially yes, because any row without a pivot would be a row of zeros, which would then just give you like 0 equals 0. So like you technically had that equation as well, but you don't need to write it out because it's just like 0 equals 0. So
Okay. And if it's a number other than one, like you have to divide so that, I mean, like for
yeah, at
the
least
reduced row echelon,
for the reduced
you
row
need it
echelon
to
form,
be
that's
one,
right.
right? Like the pivot.
That's right, yeah.
Okay.
Yes.
Okay. Sounds good. Okay.
Yeah. So then, yeah, these were all the conditions for reduced row echelon form. There is another condition which I forgot to write down, but it did occur to me when I was working through the example. If you do have any rows of 0, all the rows of zeros have to be at the very bottom of your matrix. So like, for example, in this example, this row of zeros, like technically it has to be at the very bottom. So if the rows were like rearranged, it wouldn't be an RREF anymore if the row of zeros was not at the very bottom. So that's another requirement. Okay, but so that's just kind of like a quick example of like reducing to RREF and then getting the null space from that. Yeah, so then like if you get a row of zeros, you would need to do a row swap to move it to the bottom if it like wasn't already like at the bottom, if you will. Or if you have like 2 rows of zeros, then you need to make sure those are in the last 2 rows, in the bottom 2 rows. Okay. All right. So I guess in that case, we'll go ahead and wrap up the review at this point. Okay. So I didn't quite go over everything again, but I think I went over a good portion of everything. So just be sure that, just be sure that you kind of review all the materials again. So I didn't talk about column space all that much in this review. I'm gonna say somewhat, but I wouldn't say they're really close just because I think your professors have a certain style to their questions that's hard for me to replicate, if you will, right? Because I'm not them. But at least like we'll cover similar material. But I think if you want a better sense for the types of questions you might be asked, it might be good to maybe take a look at the types of questions that were asked in your homework assignment. So some of them were kind of maybe similar to some of what I did here, but I definitely wouldn't have been able to cover the whole like variety of all the questions or the types of questions that appeared on your assignments, not in this 2.5-ish hours. Yeah. Yeah, so I don't have. Yeah, so for the other concepts that didn't go over, besides column space, I made a section on basis, well, I guess like span, linear independence, basis, and dimension. I think was another like section that was going to be on your exam. I made this section, but I don't see it in my OneNote, so maybe it didn't like save or something like that. So I'm kind of missing a section there because of that. But did I like accidentally rewrite it with this? Oh, I don't think so though, but no, because this was already, yeah, okay, yeah. So yeah, so like there's supposed to be a section about this in my OneNote, but it must not have saved somehow, so it's like not here actually. But this was like the other topic that I kind of wanted to get to. Aside from this, ideally, I would have wanted to spend more time on subspaces as well, because I know that that is kind of an area where lots of people seem to struggle. But just with the time that we had, I could only do that one example. But like, just like last time, if you guys remember, it's fine if you don't, but I can also send like, when I like email everyone with the recording and the link to the OneNote, if I have like any additional material, I will also like include that in the email, just so you guys have it available. So just kind of be on the lookout for that. Yeah, I do have like some extra material that maybe has some other examples and things like that. But aside from that, that's pretty much it though, I guess. So I'm gonna try to do it later tonight. If I can't get it done later tonight, I would do it later tomorrow morning instead. So the issue is